Welcome to the Deep Dive. Today we're setting our course really deep into the foundation of modern aircraft navigation. We're talking about the Remote Indicating Magnetic Compass System.
That's right.
And especially for those of you preparing for your ATPL theory exams, well, this system isn't just another instrument. It's actually a perfect example of engineering synthesis.
Taking the best bits of older technologies.
Exactly, and solving their, inherent flaws.
Definitely.
So we're diving deep into the architecture of this system. You might hear it called a few things.
Yeah, the gyromagnetic compass, or GMC sometimes.
Right, or remote indicating compass, slave gyro compass. They all point to the same tech.
They do.
Our mission today is basically to get you comfortable with the technical detail you need to, well, crush those complex theory questions.
Absolutely. Nail those questions.
And here's the puzzle we're sort of setting out to solve. How does a system manage to sense the Earth's magnetic field? Which is pretty subtle.
Very subtle.
Keep that heading rock steady even during, say, bumpy maneuvers, and then share that data reliably with all the other avionics.
Yeah, no, crucially.
And do all that while keeping the actual magnetic sensor, the delicate part, maybe way out on the wingtip, far from the aircraft's own electrical noise.
It's quite an elegant solution, really, a dance between physics and electronics.
Sounds like it.
And to really appreciate the cleverness of the gyromagnetic compass, the GMC, we really have to start by looking at what came before it.
The problems it solved.
Exactly. The high-stakes failures that made it necessary. Understanding those limitations, the why behind the GMC is, well, it's crucial for framing your exam answers correctly.
Okay, so where do we start? The predecessors.
Let's analyze the weaknesses of the two main systems that came before it. We'll begin with the simplest magnetic reference, the direct reading compass, or DRC.
The classic magnetic compass you see, yeah.
Pretty much. It's, magnetically accurate when the aircraft is just sitting there, static or in perfectly smooth flight. But its flaws made it essentially unusable for modern high-speed dynamic flight.
Okay.
And these shortcomings of the DRC, this is foundational knowledge. Really pay attention here for your ATPL prep.
Got it. Limitation number one.
Right. The first and probably the most notorious issue revolves around its basic design. Dynamic errors.
Dynamic error.
The magnetic element, the needle or card, is mounted pendulously. It tries to swing freely, like a pendulum, to stay aligned with gravity and the magnetic field.
Makes sense.
But during a turn, or even just acceleration or deceleration, the aircraft's inertia and the magnetic dip, that tendency of the field lines to point downwards, they conspire against it. The magnetic forces combine with what we call apparent gravity, and the result is massive, completely unreliable errors. The compass literally swings wildly. You just cannot trust the DRC reading during maneuvers.
So unusable in a turn, basically.
Fundamentally unusable for precise heading during dynamic flight, yeah.
Okay, that's a big one.
Yeah.
But you said there were others?
Oh, yes. The dynamic errors aren't the only headache. Think about where the DRC is mounted.
Right in the cockpit, usually top of the instrument panel.
Exactly. And the cockpit is, magnetically speaking, a horrible neighborhood. Just terrible.
How's that?
That proximity introduces severe deviation errors. You've got electrical currents flowing through wires, you have electric lights, motors for things like wipers or fans, radio equipment generating fields,
Lots of electronics.
and of course, just the sheer amount of ferrous metal. Think about the control yoke, the instrument panel structure itself.
Right, steel and iron components.
Precisely. All those things create their own local magnetic fields. And these local fields distort the Earth's weak magnetic field right there at the compass, sometimes quite significantly.
So the compass isn't seeing the true magnetic north, it's seeing a distorted version.
That's it, which means you need tedious compensation procedures, swinging the aircraft on the ground, installing little corrector magnets. It's a whole process.
Okay, dynamic errors, deviation errors. What's the third key limitation?
The third one, and this is absolutely vital for modern aviation, is system isolation.
Isolation, meaning?
Meaning the DRC is a completely
All right. Many thanks for listening to this free part of the ATPL Theory podcast. If you want to continue learning and access the full comprehensive guide, go to my Patreon at patreon.com/ATPLtheory or my Hero at herohero.co/ATPL. That is patreon.com/ATPLtheory or herohero.co/ATPL. Wishing you all the best